All right, welcome back, everybody. We're working on the new chapter today, and this chapter is called Coordinate Systems. And what we want to think about here is that some calculations are easier if we change our perspective. Okay, this is math teaching life lessons right here, right? Don't be afraid to change your perspective. So what is a coordinate system? A coordinate system is any collection of variables or directions even, right? Any collection of directions which intersect at right angles. And there are as many as the dimension of the space. Okay, so if we're in three dimensions, then we need a collection of three directions, and all of them need to intersect at right angles. If we're in two dimensions, we only need two which intersect at right angles, but if we're in 11 dimensions, then we need 11 directions which intersect at right angles. The special thing about coordinate systems is that no one requires that directions are straight lines. And this is the really special thing about coordinate systems. Since nobody is requiring that we choose directions to be straight lines, we have the ability to choose curved directions so long as they always intersect at right angles. And that can actually make our life easy. So curved directions are sometimes useful. Put that in quotes. Curved directions are often useful. Okay, kind of the only straight line directions that we can choose in any coordinate system are classic Cartesian coordinates, but if we want to choose some curved directions, then we can get some really useful coordinate systems out. And then the book's jumping back when you talked about complex numbers. So every complex number is represented by x plus iy, but it's also represented by r times e to the I theta. And so x and y in one case are these two variables or two directions, because the complex numbers are a two-dimensional space. These are our two dimensions in so-called Cartesian coordinates, but choosing a radius and then a rotation angle is perfectly as valid to represent z, and I think you remember that. But I'll just draw them both on the board here. So I have the complex numbers there, I have the complex numbers there. I can either choose to split my two-dimensional space up like the following, with x's and y's, and this gives us a nice little grid of coordinate representations. But I can also choose to represent by a radius and an angle. Let's choose. Okay. Theta. And notice that the lines still intersect at right angles in the r and theta version. So that's what we want to think of. This is kind of in two dimensions, we call this Cartesian and polar. Polar because it looks like we're looking at the Earth from one of the poles, and you see like your latitude and longitude lines. Cartesian, named after Descartes, of course. And it turns out what does it mean to change our perspective and make calculations easier? Well, adding complex numbers is really easy in Cartesian coordinates, but multiplying complex numbers was really easy in polar coordinates. And vice versa was not so easy. So if we decide to add polar coordinate complex numbers, it's a little tricky if the thetas aren't the same. If we try to multiply Cartesian coordinate complex numbers, it's tricky if either x or y is non-zero. So that's really what I mean to say when this explains how calculations can get easier depending on coordinate choice. Okay, so that's kind of just the intuition over why this chapter exists. We're going to jump up to 3 dimensions, and we're going to ask ourselves the questions like, in what situations are specific choices of coordinates useful in 3 dimensions? So 13.1, that's really our job for today. We're going to talk about cylindrical coordinates, and it shouldn't be a huge surprise as to what cylindrical coordinates in 3 dimensions are. These are polar coordinates in x and y. Okay, what would that be in x and y? So hence actually r and theta. So the xy plane has been developed into r and theta, but we keep z as z. So we're transforming the xy directions into now an r theta direction, but we're keeping z as z. And why is that called cylindrical? Well, if I draw my 3-dimensional plot here, and I decide to superimpose r and theta on the xy plane there, maybe r looks like this, right? So if I superimpose r and theta, but I preserve z in the vertical direction, then what I end up with is a cylinder. Okay, so that's my cylindrical coordinate system. And the way we're going to do that is we're actually not going to use r. We're going to use the Greek version of r. Greek r is, everybody's looking at it and telling me it looks like a P. That's not a P, that's rho. Rho. R-H-O. So the Greek r is the Greek letter rho, and so instead of using r, we just use rho. It's not really a big deal. Just get used to it that we're using rho instead of r in the xy plane. And just like our unit circle likes to give us, from unit circle, the x turns into cosine, the y turns into the sine. So it shouldn't be that hard to remember what these look like. But doing calculations can be a little bit tricky. So a vector now in the xy plane, or in the xyz plane, is no longer x, y, and z, but our new variables or our new directions are now the radius direction, the radial direction. Think about this as away from the z-axis. Away from the z-axis, and then this is a rotation from positive x-axis. Okay. So now our vectors are represented by a distance from the z-axis, a rotation from the positive x-axis, and that rotation takes place in the xy plane. It's a rotation from the positive x-axis, and then z remains. So now our vectors look a little bit different. And we can see how this vector might point, right? So we first determined rho as, so if this is my point, that I want the vector, the new vector, I take the distance from the z-axis. I can either calculate that up top here, or I can jump down to the xy plane and calculate rho. That's the distance from the z-axis. I then can calculate, okay, how far have I rotated from the x-axis, the positive x-axis, how far have I rotated, that's theta, and then how tall am I, and that's z. This is why we'll call it a cylindrical coordinate system. So we have a way of extracting these coordinates directly. So given x, y, z, find rho theta z. And the way we do it is we say rho theta z equals, rho is always root x squared plus y squared. Theta is always arctan. Now recall arctan and tan inverse are the same. Arctan y over x, and then z thankfully remains. We do have to be a little bit careful about the arctan, okay? We might have to add pi to it when x is negative. That's just something that you can do if you actually put the work in to verify. You might have to add pi. Your calculator will give you a somewhat nonsense answer if you put a negative x in there, and so you just add pi and get something better out of it. But that's how we can convert between the two of them. And I love this part because we're getting to a point in the book where the book is still maybe a little unfinished. Insert figure. Okay, so let's move onwards to actually working with the cylindrical coordinates. So everything up here, if you want to read the book, you go right ahead and do the exercises. I'm not that worried about it. It's to give you a little extra intuition. I would rather that we actually learn how to use these in a calculus setting. So of course we can calculate a curve. just as we did prior, instead of the curve depending on x, y, and z, it now depends on rho, theta, and z, and each of those evolve over time. Very standard. Now, scalar fields have inputs of rho, theta, and z, and vector fields have inputs of rho, theta, and z. Okay, so you could either represent this now as the vector v1 of rho, theta, and z in the x direction, v2 of rho, theta, z in the y direction, v3 of rho, theta, z in the z direction, or you could represent them actually as a rho vector, a theta vector, and a z vector. So it's useful actually to use the second case if we're going to stick ourselves in cylindrical coordinates. But you can definitely define either if you want to. There's nothing actually requiring that you choose one versus the other. But you do have to specify and just make sure. So let's look at an example, a cylindrical curve. So let's say gamma of t is cos t sine t 0, the first time I read it. But if I then want to shift to cylindrical coordinates, I can. So let's take this gamma and shift gamma to cylindrical coordinates. Shift to cylindrical. What I'm going to do is I'm going to take, so I'll call this gamma Cartesian, and now gamma cylindrical of t. I'm going to take gamma 1 Cartesian squared plus gamma 2 Cartesian squared. I'm going to take the square root of that because that's x squared plus y squared. Then I'm going to take the arctan of gamma 2 Cartesian divided by gamma 1 Cartesian, and z thankfully remains the same. So this is the process I'm going to go about to find the cylindrical version of gamma. If I take gamma 1 and square it, let's see this really quick, gamma cylindrical. Gamma 1 squared is cosine squared. Gamma 2 squared is sine squared. I take a square root of that to get the first entry. I then take arctan of gamma 2, which is sine, divided by gamma 1, which is cosine. And then I keep the last one the same. Sorry, this is still going to be gamma 3 here. Okay, so if I simplify the cosine and sine squared terms there, I just get 1. If I simplify arctan, right, recall that sine divided by cosine is tangent, so arctan of tangent just gives me t, and the z term is 0. So that's gamma in cylindrical coordinates. Let's scroll down and see if I did that correctly. There it is, 1t0. Okay, we can take a derivative of gamma, but we have to be careful about how these derivatives exist. So you're going to notice something special in the definition of the derivative of gamma here. Rho depends on time, you can take a derivative of that. Theta depends on time, and you can take a derivative of that. And z depends on time, you can take a derivative of that. But it turns out that we actually have to multiply by rho on specifically the theta term to talk about the derivative there. And the reason for this is that angular velocity depends on the radius. And I think everybody agrees with me that if I am traveling around a really big circle or a really small circle at a fixed frequency, if it takes me 1 minute to run around a quarter-mile track, or it takes me 1 minute to run around an eighth-mile track, then I was running a lot faster around the quarter-mile track. So the larger the radius is, the faster my angular velocity is. And that's why we pick up rho right there. So that's just something to keep in mind, because now all of a sudden derivatives are not quite as easy to calculate. And let's maybe write it down this way too. So gamma dot cylindrical is rho dot rho theta dot and then z dot. That's another way of interpreting that. These all depend on time. So just keep that in mind. We're multiplying the theta term by rho if we take a derivative. And then calculating acceleration, we actually have to put even more work in. Calculating acceleration, we have the acceleration in rho, which makes perfect sense. Here we've taken a product rule, which makes sense as well. And then in Z we have just this. So I want to mention that the typo is here. It's going to be rho for each of these r's as well. That's rho of t in both cases there. And of course the thetas all depend on t as well. So each of those r's are actually rhos, and we end up with this nice little term in our first direction, this lovely term in our second, and of course z is very easy to calculate. In cylindrical coordinates, then, that means that the way our infinitesimal length, or rather the magnitude of the derivative looks, also changes a little bit. So these are just all things to keep in mind when we're working in cylindrical coordinates. You can always refer to the section of the book when you're completing your problems as well. So let's actually do some work with this. So let's start with the scalar field, z over root x squared plus y squared, and I'm already thinking to myself, looking at this, that this might be easier to represent in cylindrical coordinates because root x squared plus y squared actually is rho. And so this would look like z over rho in cylindrical coordinates. Okay, so that's really the idea as to why this might be a good choice for this particular scalar field. Okay, so we're talking about unit vector fields now, and I think this is a weird, maybe a little bit of a weird name for what we're actually trying to talk about. What we want to describe is a vector field with unit vectors all pointing in a given direction, as in the direction that we're using in our coordinate system. So in this case, in the direction of rho, in the direction of theta, in the direction of z. What does that mean in some sort of broader coordinate system? Well, let's think about it. Let's draw our three-dimensional space. And recall rho is pointing in the direction away from the z-axis. So then, like, a unit vector field in rho, aside from directly at 0, is just the vector field which points away from the z-axis in every direction. And they're all unit vectors. So that's what we mean by unit vector. This is like my unit vector rho vector field. Theta, on the other hand, you'll recall, is like this rotation from the positive x-axis. So theta is probably doing something like this, is kind of the unit vector field for theta. So you can just construct a unit vector field for both rho and theta, where they're all unit vectors pointing in their respective directions. I don't think anyone's going to get surprised when I draw the z unit vector field here. That's just the vector field pointing in the vertical direction. Okay, so there's z. So then intuitively, how should we construct these? Well, we can either do it with the following language. We can do it with the language of a vector field in rho theta z, then the rho unit vector field, which I'll just put a rho there. That's just 1, 0, 0. But maybe I want to represent that as v rho of x, y, z, and that's maybe a little bit trickier. What does that look like for rho? And that's where we have the following. So it turns out we move in the x direction and divide by the radius. We move in the y direction and we divide by the radius. And that's not that tricky, but it's just something to keep in mind when we're working in cylindrical coordinates. So it's x divided by root x squared plus y squared, y divided by root x squared plus y squared, and then z is 0 in this vector field. So there's the unit vector field in rho. Just kind of, you could freeze frame that and memorize it if you want to. Scroll down, we can see the unit vector in theta, unit vector field in theta. Oh, we can represent that, by the way, with a rho hat. That's the way I would probably represent that in terms of x, y, and z. Unit vector field in theta, theta hat in terms of x, y, z. Written as x, y, z is in the form negative y divided by the radius and x divided by the radius. And this makes a lot of sense because we've already seen that this is kind of your generic vector field which describes rotation. It has a non-zero curl, but that's just something to write down as well. And then z, no surprise, that's just going to be 0, 0, 1, which is our favorite vector field in these cases. But those are just good to keep in mind. Anyway, I'm going to stop there for today, and then we'll move on to some more calculus for the next video. Thanks. See ya.